All right, greetings everyone. The purpose of this video is to go over section 3.5 from our textbook. And as you'll note on the slide here, in section 3.5, we're not actually going to be learning anything new, or at least a new integration technique. The idea here is to look at the integration techniques we've learned thus far and to try to decide when would we use each and how would we know when to use each of them. Okay, so let's take a look at this. So what I have here is on the left-hand column, I have a list of all the different integration techniques we've looked at thus far. And on the right-hand side, I have an integral that relates to those. Okay, so let's go through them one by one. So the first is algebraic manipulation or direct integration. And these are the integrals that we can just look at and know how to do directly by finding antiderivatives. Some examples of that might be something if we have like integral of x squared dx, or if we have an integral of like 3 dx, or integral maybe something 3t dt. Those are all things that we can use our power rule for, or even something like if we have the integral of cosine of theta d theta. Those are all ones that, again, using antiderivatives, we can find them right away. Now with this one here, when we look at that at first, it may seem kind of scary because we have the root x in the denominator, the x to the fourth plus 7 on the top, and you might be thinking, man, I need to do some sort of crazy substitution or something like that. But this is an example of the one that's where it says algebraic manipulation. Because what we can do with this integral is rewrite it. Since we have two things being added in the numerator and just a single denominator, we could write this as x to the fourth over square root of x plus 7 over square root of x dx. And now we see that in this case, this part right here, this 7 over root x, we could evaluate or find the antiderivative of using our power rule. The x to the fourth over square root of x might at first look a little scary, but note I can rewrite this as x to the fourth over x to the 1/2. And in this case, we can subtract the two exponents there and make this x to the 3.5 or x to the 7 over 2. Okay, and so then that first integral there just becomes another power rule. So again, when we see algebraic manipulation, that means we could do some sort of thing, move some stuff around to then help us evaluate the integral. Okay, and we're not going to do those right now. We're just going to identify how we knew to use that. Second one is substitution. And the integral we're given is integral of y over y squared plus 1. And why, or how do we know this is substitution? Well, if I look at one of the expressions in there, the y squared plus 1, I know that if I take the derivative of that, so we get du equals 2y dy. And if I move the 2 over, we have 1/2 du equals y dy. dy, not dx. And from there, we know that, oh, this y dy occurs in the integral, right? So we see the derivative of one of the expressions appears in the integral. And so that's how we would know to use substitution. Right, integration by parts. This is one where we're looking for a u and a dv. And so typically there's going to be two functions being multiplied in our integral. And that's what we see with the example here, the t squared and sine of t. Okay, so we have t squared times sine of t dt. So those could be our u and our dv. Remember also our acronym, our LIATE. It tells us kind of an order for thinking about how to determine what to choose for u and what we look for first. So the first ones, remember, are logarithms. Second ones are inverse trig. If we don't find any logarithms, if there's no inverse logs or inverse trig functions, we'll look for algebraic, which are things like x squared, square root of x, those sorts of things. None of the first three, then we look for trigonometric. And remember, these are different than inverse trig because inverse trig is something like inverse sine, inverse tangent, arcsine, arctan. Trig is the non-inverses, right? So sine, cosine, cosecant, those sorts of things. And the last choice is always the exponential, right? That's e to the x. And that's usually our last choice because it's such an easy function to integrate that we often want to choose that for dv. All right, trig substitution. So remember, when we're looking at that, we're looking for the one of those three forms we have. So the square root of a squared minus x squared, square root of x squared minus a squared, or square root of a squared plus x squared. Okay, or x squared plus a squared, which should be the same thing. Anytime we see one of those, then we would go ahead and use a trig substitution, which is what we see here, right? We have square root of 16 minus x squared. And so that's that form a squared minus x squared. So we use trig sub. For partial fractions, in that case, we're looking for a denominator that we can factor and break into parts. So here we see that this x squared plus 13x plus 36, that factors into x plus 4 times x plus 9 with our x plus 6 in the numerator. And so we can go ahead and try to rewrite that in a form of a over x plus 4 plus b over x plus 9 so that we can integrate that a little bit easier. And then finally, table of integrals. Well, those are the ones where none of our other techniques work, right? So when we look at an example like this, the integral of 2v times tangent cubed v squared dv. You know, this is one where we might try u substitution, right? Because I see the v squared here in the 2v. So I might say something like u equals v squared, which gives us du equals 2v dv. But if we substitute that in now, our integral becomes tangent cubed of u du, since the 2v dv will be taken or have the du substituted there. But then tangent cubed is something that we, again, have not spent any time or do not have a technique for integrating. So in that case, we would go ahead and turn to the table of integrals to help us find that. All right. I would encourage you to maybe make your own list. So list down all of these integration techniques and think about how do you identify that you need to use each technique. All right, that's it for now. Thank you for watching.